So for this problem, we're going to look at a series of statements that we need to convert into mathematical notation for some differential equations. Typically, this might be at the start of a question, which you then go on to solve the differential equations, but we'll look at how to solve those in later problems. So the first one says the rate of decrease of a mass m of a ball of snow is proportional to the mass of snow remaining at any instant. So let's break this up into what this means. Well, you've got the rate. Now, if it's mentioning about rate, you should be thinking, well, it's a rate of change, really. And if it's a rate of change, this means we're going to have some kind of differential there. And specifically, if it's a rate of change, you're differentiating with respect to time. So it's going to have a dt in the denominator. And for this problem, the thing that is going to be changing is the mass of the ball of snow. So in other words, we want dm, which is the thing that is changing, with respect to time, so it's dm by dt. That's our differential. Now, it tells us that it is proportional, so we can use the proportionality symbol to start with. We'll get rid of that in a little bit, but we can start off with the proportionality symbol. And we are told that it is proportional to the mass of snow remaining at any instant. So it's proportional to the mass of the snow. And we're actually told that it is a decrease. So it's going down. So actually, we can say it's proportional to the minus of the mass of snow. Okay, because it's a decrease. Now, we don't like the proportionality symbol, so actually we can get rid of that and we can make this into an equal symbol instead. And all we have to do is add a constant k, where k is, in this case, a positive proportionality constant. Now, we'd normally stop there. That's our actual differential that we want. However, because we've actually defined a couple of variables there, we need to actually state what they are. Now, m is given in the question, so you don't need to state that, but t is not, so we need to say that t is our time, and it's useful to point out k, which is our positive proportionality constant. Now, alternatively, you could have this as just equal to km, but k would have to be a negative proportionality constant there, which is why defining it is very important, so the examiner understands that you know what's actually happening here, whether it's a decrease or an increase. So for part B, then we've got the gradient of a curve at each point xy on the curve is equal to the square of the sum of the coordinates at that point. So this one's actually quite a nice one. Well, our first keyword is gradient, and we're talking about gradients of curves. We're given the points in terms of x and y, so you should be thinking gradient, differential, specifically dy by dx. And indeed, that is our differential. So dy by dx. We are then told that it is equal to, so we don't need to deal with the proportionality, we can straight away say that this is equal to something. And then we are told that it is the square of the sum of the coordinates at that point. Well, that's just a fancy way of saying that you've got the sum of the coordinates. Our coordinates are x, y, and if it's sum, it means it's a plus, it's an addition. So we've got x plus y. And you've got the square of the sum, so it just means that we need to square that expression. So whatever x plus y is, square it, and that's dy by dx. So that's quite a nice one. Then part C, we've got a body falls from rest in a medium, which causes the velocity to decrease at a rate proportional to the velocity. So again, we've got a little bit of terminology in here, and we've got to look at what's happening. And a body falls from rest in a medium which causes the velocity. So the velocity is the thing that is going to change, it decreases, and it is at a rate, so it is going to decrease with respect to time if it's a rate. So our differential becomes dv by dt. It is proportional to, so we need a proportionality symbol, to the velocity. So again, it's going to be proportional to the velocity, and specifically it is a decrease, so it's going to be proportional to the negative velocity. We'll take care of that in a second. But we don't like the proportionality symbol, so let's do what we did in part A. So let's replace that with an equal to, and we also need a constant of proportionality there, so minus k v, and then we just need to define some of our variables then. So we use v for velocity, and k, once again, because we have a minus there, that is a positive proportionality constant. And finally, we've also got t there, so let's just define that as our time. Now, just going back to b, we didn't need to define our x and y because they are already defined in the question, just like mass was in the first part. Okay, so if the variable is already defined, then you do not need to define it again. But if you are going to use a new letter, just make sure that you write out what that letter actually stands for. That's very important, so that the examiner can definitely not deduct any marks then.